All right, so we're going to talk about rolling on a ramp. So in your previous video, we learned about what rolling is. Rolling is the combination of translational and rotational motion, where a rolling object has both an angular speed and its center of mass is translating, so that we can assume that the velocity of the center of mass, which we usually just call v, they usually don't say VCM in a problem, that's just the linear speed v, is equal to r times omega, where r is the radius here of our rolling object. In this case, we're going to look at a solid cylinder with mass m and radius of r, and we're going to assume that it's given some initial angular speed and that and some linear speed. So this thing is already rolling when it's going to encounter a hill, like a ramp here. So we're going to have some sort of inclined ramp at some angle theta. And what we're going to do here is we're going to take a look at the linear and angular acceleration of the rolling object. Next unit, when we talk about energy, we'll talk more about speed and so forth. But we're going to start here with the dynamics about what's actually going on here. So when it's on the flat surface, when we look at the forces that are acting, there is going to be a gravitational force acting at the center of mass. There is going to be a normal force acting. And generally what we assume is that this surface here, when it's flat, is frictionless. But when we hit this surface, we're going to assume that this surface here has friction. But in order to roll without slipping, we assume no losses of energy to heat. So basically our mechanical energy would still be conserved. So it has to be frictionless down here, because if there was a friction force either going backwards or forwards, then you would have a net force in acting on this to the left or right, and that would cause it to slow down or speed up. So we do have to assume that the horizontal portion is frictionless. But then we're going to assume that in order for it to change its rotation, there has to be friction. Now, if this is frictionless, then basically the rotation is not going to change. So you're going to have problems with that, because without friction, we're going to have no torque. So generally, in order to have a torque acting, you are going to need to have friction. That's what we're talking about here. So if this was a frictionless surface, you would treat it more along the lines of what was happening kind of before. A little trickier, but it would still work. You'd be able to solve the problem. But we're going to consider the fact that there is friction on this ramp. So, if there's friction on this ramp, we need to consider what forces are acting. So that you're going to have a gravitational force down. And you're going to have a normal force. Now I'm doing an extended body diagram. So my normal force is acting here. And remember that normal force is actually going to balance the y component of gravity. It's not going to be completely balancing all of gravity. So then, if there's friction, this thing's going to slow down as it moves up the ramp. It's going to slow both its linear motion and its angular motion. So in order for its angular motion to change, there has to be a net torque. Well, the problem here is the reason that, well, not really a problem, but the reason there has to be friction is, let's look at these normal force of gravity and look at torque. So the axis of rotation is going to be the center of the cylinder. So when I look at gravitational force, the gravitational force can have no torque because it is acting at the axis of rotation. So the lever arm would be 0. If I look at normal force, the torque to the normal force is also 0. And it has a lever arm R, but the normal force is parallel to the lever arm, so there is no torque. So if this thing is going to slow its roll, it's going to slow its rotation, there has to be another force that is exerting torque. Now the question is, what direction does that torque have to point? So Well, we have to assume that some rotational kinematics. So if this thing is rolling up the ramp with an angular speed there, if it is going to slow down its angular speed, then that means there has to be an angular acceleration in the opposite direction of the angular speed. So the angular acceleration has to be in the opposite direction as omega if you're slowing down. So if we're going up the ramp, we're going to slow down. We're going to take a look afterwards. If we're rolling down the ramp, well then has to be the same direction as omega if you are speeding up. So if we were going down the ramp, we'd be speeding up. So therefore, they'd have to be in the same direction. So then we have to figure out, okay, we know that it's friction, because that's the only possible force that could be causing any action. And friction is going to act at the point of contact. Now, like we said with rolling, we assume there's only one point of contact while rolling. So the question is, does the friction point up the ramp, or does the friction point down the ramp? Which is it? Well, we know that the angular acceleration is down the ramp. So if I want my angular acceleration to, not down the ramp, but to be in the counterclockwise direction, then if I were to use the right hand rule and picture the heel of my hand being at the, I'm going to draw it again here, so I can actually reach this. So I want to figure out where, so I've got a lever arm R here for my axis of rotation. I need to figure out which way friction points. So if I picture the heel of my hand being the axis of rotation, and I point my fingers in the direction of R, then I want my hand, when I rotate it, to go this way. So that means that in order for that to happen, in order to get my hand to curl in that direction, my friction force actually has to point up the ramp. Because if I do my fingers like that, rotate my palm, curl my fingers, that gives me the angular acceleration that I need. If it were pointing down the ramp, then that would mean that my angular acceleration would be pointing the opposite direction, and that would mean I was speeding up the ramp. And it is actually possible for that to happen. If there was like a little hamster inside of here, and that little fuzzy hamster, oh, I cannot draw a hamster. But there's a little hamster inside of this ball, and that little hamster was running inside of that ball. It's possible that that hamster would be causing, with his motion, a friction force backwards, because he'd be pushing down and down, and he'd be trying to go up, and it would be pushing down, and that would actually cause an angular acceleration in the opposite direction, so that if it was rolling up the ramp, okay, with omega going that direction, and the hamster was providing an additional angular acceleration up the ramp, then this could actually speed up the ramp. But unless there's a little hamster or some sort of like motorized like wheel, like a toy car type situation, then it's impossible for the angular acceleration to be in the same direction as omega, which means that our friction force has to be up the ramp. Okay, so that tells us that our friction force must be up the ramp. And it is parallel to the ramp. So it actually makes a nice 90-degree angle with the lever arm, so that the torque due to friction is just going to be the friction force times R. So if this thing is going to be slowing down angularly, it is also going to be slowing down linearly. Because if VCM is equal to R omega, the linear acceleration of the center of mass is also going to equal R times alpha. So that means that in terms of the linear motion, we already know where that acceleration points. Because if we're moving up the ramp and we're slowing down, our linear acceleration has to point down the ramp. So we have both linear and rotational motion going on. So we can write equations for net force and equations for net torque to solve this problem. And we want to find essentially what is that new linear acceleration? Because I know that if this was a frictionless ramp, with no rotation, so that this hoop or it's a cylinder in this case, if this cylinder was just sliding, this was just sliding up the ramp, the linear acceleration would be g sine theta. We did that last semester. So if this thing is not rolling, if it's just sliding, if it's just translating up the ramp, then its acceleration would be g sine theta. So we actually want to find the acceleration here in this case. So what we're going to do is we're going to write equations for net force and net torque. So in terms of net force, I'm going to kind of look back at kind of a just a plain free body diagram, because it's a lot easier to do force with a free body diagram. So I would have friction, I would have normal force, and I would have a gravitational force. So I would have rotated my axes. I know that my linear acceleration is down the ramp, so I'm going to make this the positive x direction. This friction force is therefore drawn too large. So make my friction force a little smaller. And then I would want to resolve my gravitational force into components. So I would have an Fg in the y direction and an Fg in the x direction. Fgx would be pointing down the ramp. So I could write a net force in the x direction, which would be my Fgx minus my friction force is going to equal m times a. And that is a for my center of mass. That's my linear acceleration. I could do an equation in the y dimension that would just tell me that Fgy equals Fn, which we're not going to need in this case. So if I wanted to then sub in what I know if that's my angle theta, that this is my angle theta. So Fgx is going to be mg sine theta. And I have minus friction force is equal to m times a. Now, in this case, we do not know the coefficient of friction. So mu is unknown. And it's usually unknown in these cases. Because it's not going to be the coefficient of static friction. It's not going to be the coefficient of, well, it is technically a coefficient of static friction. Because remember, we assume that there's only one point of contact, so it can't slide. We are assuming no slipping, so it's actually a coefficient of static friction, but it's going to be a particular coefficient of friction between those surfaces that is possible for that. So you would have to have like the perfect valued coefficient in order for this to roll without slipping. You could find that. It is possible for you to figure out what that coefficient is, but they usually don't tell it to you. But it's definitely not kinetic friction. So that means I cannot use any of the friction force is equal to mu Fn, in particular because since this is a static friction force, this is only true if you're at the slipping point. Because you have to get that maximum static friction. And since we want to roll without slipping, we don't want to be at the slipping point. So therefore, this equation doesn't hold. So we actually can't find the coefficient unless you're actually at that point. So unless I actually tell you you were at the slipping point, you cannot find that coefficient of static friction. Which means I need to find another way to find this friction force because I need to find acceleration. That's my goal. This friction force is a huge unknown. Well, friction is what's causing my torque. So I can write a net torque equation. So my net torque is going to be caused solely by friction. So that is going to be the torque due to friction, and that's going to equal I times alpha. So my torque due to friction is just going to be my friction force times R, because I'm assuming that they are making a 90-degree angle between the lever arm and the force. I'm doing a solid cylinder, so my moment of inertia is going to be 1/2 mr squared. And the reason I tend to like to do my example problems with a cylinder rather than a hoop is I like to be able to see that coefficient. This could also have been a sphere or a hollow sphere, solid sphere, any of those situations. In that case, this coefficient would change. The rest of the process would be the same. So the first thing I notice is I do lose one of the r's from this equation. So I find that my friction force is equal to 1/2 mr alpha. So I can actually sub in to my friction. But now what I've done is I've actually subbed in another unknown because alpha is now unknown. But I can always use this, that my linear acceleration is equal to r times alpha. So I can sub in that alpha is going to be r times, a over r. So my friction force is going to be 1/2 mr times a over r. So the other r cancels. So the radius of this wheel has no factor here. So my friction force is going to equal 1/2 m times a. So I can then take that here and sub in. I'm going to have to make a little space here. And I sub in and I get mg sine theta minus 1/2 of ma is equal to ma. Since this is a single object, these m's are the same m's. Those are the same a's, a for the center of mass. And then I could group those a's together. So I get mg sine theta is equal to 1/2 of ma plus ma. So if I group that, I get mg sine theta is equal to 3/2 of ma. Notice that the mass actually cancels out as well. So actually the mass and the radius has no bearing whatsoever. So any solid cylinder of any mass and any radius is going to end up with the same acceleration on this ramp. So solving for acceleration, I can move the 3/2 to the other side. So I get acceleration is 2/3 of g sine theta. So the only difference between our theoretical model, if it was frictionless, is this 2/3. And that 2/3 partially comes from the coefficient. So that if you had a different coefficient, so if this was a sphere, hollow or solid, or if it was a hoop, you would still be a fraction of g sine theta. That fraction would still always be less than 1. Because if this was, say, a hoop, that wouldn't be a 1/2, it would just be a 1 for a hoop. You would end up with ma plus ma, so you'd end up with 2ma. So if this was a hoop, you'd end up with 1/2 g sine theta. So as soon as you introduce this idea of friction so that you're causing a torque, you're going to reduce the linear acceleration. And that's because instead of just having linear acceleration, some of that motion is being used to change, some of the torque and force is being used to kind of adjust the angular motion as well. So that's how you could find the angular acceleration of an object rolling up a ramp. Now, I don't know if you remember this, but if I had a frictionless ramp, and this object was sliding, so say it's frictionless, so there's no rotation. The acceleration as this thing goes up the ramp versus down the ramp is the same. The acceleration on the ramp was g sine theta. It didn't matter whether you're going up or down, because whether you were going up or down, that x component of gravity was always going to have a magnitude of mg sine theta. Because the only difference is if this was a frictionless ramp, this would be 0. So if it was a frictionless ramp, then you would end up with mg sine theta is equal to ma, the mass would cancel, you get a is g sine theta. It didn't matter whether this is moving up or down. You always get the same acceleration. And if we were go through and look, we need to figure out, is this the same when we have rolling? Is the acceleration of an object rolling up a ramp the same as the acceleration of the object rolling down the ramp? So if we were rolling down the ramp, we would assume that maybe we started at rest somewhere, so that way we're going to start speeding up. So you're going to have a linear speed. That would be your VCM, that speed of the center of mass would be going down. This thing would be rolling in that same direction. So that if we went that way, we'd have to be rolling that way. So this is actually the different direction of omega than it was when we were going up the ramp. So I know that my linear acceleration has to be down the ramp. I know that my linear acceleration has to be down the ramp, because if it's going to speed up linearly, that linear acceleration has to be in the same direction as my velocity of my center of mass. Now, in terms of the rotation, if I'm speeding up linearly, I also have to be speeding up angularly, so that I'm going to have an angular acceleration alpha that is in the same direction as my angular velocity. Now, what does that mean in terms of forces? Well, we still have a gravitational force pointing straight down. We still have a normal force parallel to the ramp. And the gravitational force still exerts no torque. The normal force still exerts no torque. The normal force because it's parallel to R, the gravitational force because it's at the axis of rotation. So the only way we can have an angular acceleration is if there was friction causing torque. But what direction does that need to be? Well, if we take a look, okay, at that hoop again here, if this is my axis of rotation, I know that friction acts at the point of contact with the wheel. There's only one point of contact despite my horrible picture here. And that is going to be the lever arm direction from the axis rotation out. I want my angular acceleration to be in that direction. So if I take my fingers and I want to rotate my palm so that I can curl that way, that tells me that my friction force is still up the ramp. So whether I'm rolling down the ramp or rolling up the ramp, my angular acceleration is always in the same direction. Because if I'm rolling up the ramp, my omega would be going, in this case, the clockwise direction. So when I'm going up the ramp, I'm slowing. So that means that my angular acceleration would have to be so my angular velocity when I'm going up the ramp is in that direction, it's clockwise direction. So I'm slowing, so that means that my angular acceleration has to be in the opposite direction as whatever the angular velocity was. So in this case, the angular velocity was clockwise, so my angular acceleration had to be counterclockwise. When I'm going down the ramp, my omega when I go down the ramp is going to have to be related to a what direction is that? That is a counterclockwise direction. I'm speeding up, which means alpha has to be in the same direction. So because my omega was in the counterclockwise direction, my angular acceleration also has to be in the counterclockwise direction. So in this case, no matter whether I'm going up or down the ramp, this angular acceleration is in the same direction, which means my friction force always points up the ramp. In all cases. So since the friction force points up the ramp, that means that there is absolutely no difference in my net force or net torque equations when I'm going up the ramp versus down the ramp. So that means that my linear and angular accelerations are the same whether I go up the ramp or down the ramp. So I don't need to go and solve another problem. If this was rolling down the ramp, it would be the exact same acceleration. It's just instead of causing the object to slow down, that acceleration would be causing the object to speed up.